So we have discussed how valence electrons are the important electrons because they're in the outermost shell, and when two atoms come together, it is those electrons that will first interact. So those are the ones that determine the reactivity of different elements. These valence electrons only consist of S and P electrons because the D and the F are always filling in a sublevel below the S and the P. So the maximum you can have is 8 valence electrons, since the S and P hold a total of 8, 2 for the S and 6 for the P. So here you can see that visually. Neon, the S and the P of the two sub energy level are the highest, or the outermost electrons. For argon, it's the S and P in the third energy level. For krypton, even though there are d electrons, those electrons are in the third energy level. The S and P are in the fourth energy level. For xenon, the S and P are in the fifth energy level. The D is in the fourth energy level, and so on. So the maximum you can have is 8 valence electron, also known as an octet by some. I don't love that because helium doesn't have an octet. But anyway, so outermost electrons is what reacts, is the reason atoms in the same group react in a similar manner. So all of group one has 1 valence electron, and that's why they react in a similar manner. And that's how Mendeleev and all the other people who threw together the periodic table knew to put everything in group one in the same group, because they all reacted in a similar manner. Group two has 2 valence electrons. The transition metals will vary based on what's most stable. If you have to guess, it's a good rule of thumb that they'll have 2 valence electrons, but we're not really going to worry about the transition metals at this point. Moving on to group 13, those will have 3 valence electrons. So this is actually group 13, not 3. This is group 14, 15. But yes, the valence electrons go up to 8 based on how many S and P electrons they have in their outermost shell. All right. So because of that, and of course the noble gases are the Kardashians and everything, having 8 valence electrons is sort of the goal. So Lewis structures will give you the element symbol, and then you're going to surround that symbol by the dots based on how many valence electrons there are, and you're going to put 2 per side. So notice group 1 has hydrogen, lithium, sodium, potassium, right? So all of these have 1 dot around them because they only have 1 valence electron, and the ones next to those have 2. Again, the transition metals are sort of ignored a little. Group 13 have 3, so this is group 13, this is group 14, this is group 15, right? So the boron group has 3 valence electrons, the carbon group has 4, the nitrogen group has 5, the oxygen group has 6, the fluorine halogens have 7, and then the noble gases have 8, except for helium, which has 2. All right. So this is just another way to show these elements. So you put the symbol in the middle, and then you surround it with valence electrons. You can't exceed 8, and there's 4 sides, and you can put 2 on each side, north, south, east, and west. So there you have it. All right. So the other thing we talked about is if there's a first ionization energy, then maybe there's a second ionization energy. Otherwise, why would you call it, right? You wouldn't call something part 1 unless there was a part 2 coming. So here is the second and third ionization energy. So let's talk about lithium. So lithium has a electron configuration 1s2, 2s1. And for that to lose an electron to become lithium plus 1, that's now going to be, actually I meant to do that in a different color. Let's pretend I did that in a different color. So lithium plus 1 has an electron configuration of 1s2 because it lost that 2s1. So then it also has 1 electron that got taken away. So this is a nice stable helium electron configuration. So lithium is pretty happy to have that happen. And so the first ionization energy would be pretty low comparatively because it just became like helium. Now, if we try to take a second electron away from that, and then now we're going to make it like, so lithium plus 2. So lithium plus 1 was the nice stable helium, and now as lithium plus 2, it's 1s1. So you broke up the band. You just made lithium no longer a noble gas outfit. And so this ionization energy, the second ionization energy, would be high. So that would be the second ionization energy. So if there's a first ionization energy, that's going to make it a positive ion from a neutral, and the second ionization energy is going to take the +1 and make it into a +2. And so what you can see here, uh, sodium to start has a lower first ionization energy than magnesium, because sodium is going to be losing this 3s1, and that's the only electron. It's highly shielded from the nucleus by the 1s2, 2s2, 2p6, and so it is not unhappy to get rid of it. And when it gets rid of it, look at what happened. Sodium is now a noble gas in the electron outfit it's wearing. So it's lower than what magnesium has. Magnesium, you're breaking up a 3s2, and by breaking up that 3s2, you're breaking up a full subshell, which isn't great. So magnesium is going to have a slightly higher one than sodium. But when you're taking a second one away, so that's what this one is, the second ionization energy, now magnesium has that 3s1 hanging out, and it would love to get rid of that to be like a noble gas. So when you see this second ionization energy, for sodium, it's much larger. Here's sodium. Because with sodium, you're breaking up the noble gas neon electron configuration, whereas magnesium, you're achieving the noble gas neon by dropping that 3s1. Now what's left over is neon. So the second ionization energy is much lower for magnesium than it is for sodium. And this, in fact, is why we see the cations formed that we do. So for the first ionization energy, hydrogen loses its one electron, and there is no such thing as a second ionization energy for hydrogen. So starting at helium, losing that perfect helium ionization energy, losing that perfect helium electron configuration is costly. The second one is also costly, but comparatively not. Well, actually, if you notice, this basically looks the same. It just got shifted over. So this one here is the second ionization energy, and the other one is the first ionization energy. So you can see they have a similar shape, but they just got shifted over. Anyway, so instead of the noble gases, as with the first ionization energy being the biggest deals, what you'll see with the second ionization energy, the biggest deals are the alkali metals. So lithium, sodium, and potassium have the highest second ionization energy, because after losing one electron, those are going to be like the noble gases. So one last thing here. So notice here's the line between somewhat simple and 10 times as hard. So that's why sodium ends up as an Na+1 ion, because losing one is not hard, losing two is difficult. Magnesium is a +2 ion, because losing one and losing two aren't awful. Losing the second electron is only twice as much as the first, but losing that third one now is going to be 7 times as much. And then for aluminum, aluminum is stable as a +3 ion, because losing that first one, that second one, that third one, the jump is not as significant as between the third and the fourth, where you're going almost by 6 times as much. So aluminum stops here after losing 3 electrons, magnesium stops here after losing 2 electrons, and sodium stops there after losing 1 electron. And that is first and second ionization energy. Also, I'm using the word potentially. You've heard it, that when things are positive, they're called cations. Here is a cat. Notice a cat has paws, and because it has paws, cations are positive. So anything that has a positive charge, lithium +1, magnesium +2, aluminum +3, all those, right? If there's iron +2, anything like that, those are all considered cations because they have a positive charge. And this is just vernacular you need to know. If there's a name for the positive ones, there must be a name for the negative ones. The negative name is called anions. Anions are negative. Think of Anakin Skywalker, or just anger in general, right? Anions, anger, that's a negative thing. So anything that has a negative charge would be considered an anion. So There you go. There's not as many anions as there are cations. All right, which is brought up here. So metals form cations. They're the ones that lose electrons. And you can see here a bunch of just popular metal cations around. The nonmetals is a much smaller piece of the pie. So that's over this side. And the nonmetals form anions. And that was the